This is an example of a sequential design using memory microprogramming. So in this example, we're going to design a mechanism that counts coins, and we are assuming that they're going to be nickels and dimes. Now suppose that the target machine vends items that cost 20 cents. A user enters nickels and dimes in a slot, one after the other. The mechanism that we seek to design will release an item when the coins which have been entered amount to 20 cents. The slot is assumed to have a sensor to sense the size of the coin and produces two signals, N and D. So there are two signals produced, two wires, which will signify respectively that a nickel or a dime has been put in the slot. These signals will be input to our system, the one that we seek to design, and the output of our design will be a single signal that activates the delivery mechanism. So we will start with a description of how the intended system is supposed to behave. This description will be given in terms of a state transition diagram, which is a formal specification of the intended operation. So the first step is to put down an initial state. That's the resting state from where the system is going to start. Then we have to specify from this state what happens when every particular input possibly arrives. In this case, we draw an arc to indicate that we're going to go to another state after a nickel has been entered. Now, this specifies the input that causes this transition from this state to another state. We also specify the output. So this machine is going to be a mealy machine, specifying the outputs on the transitions, and at this point our system is producing a 0. It's not producing any activation to the release mechanism yet. So in this new state, S1, the system remembers, by virtue of being in that state, that it has received a nickel. So from there, as you can imagine, we keep going to new states, and with every new state the system remembers. In other words, by being in that particular state, it is encoded that the system has received a certain amount of money. So in this case, by being in state S2, the system practically encodes the fact that it has received 2 nickels. So this continues on like that, going to another state and another state until we have the 20 cents. So at this point we have received 1, 2, 3, 4 nickels, so we have 20 cents. So as you see, this transition is different than the previous ones in that the system is producing an output of 1, which basically activates the mechanism that releases the money, the item. Now we have to specify from every one of these states that we created what will happen under any possible input. So all of these states specify what happens when a nickel is received, but we have to specify what happens when dimes arrive as well. So this is the case where from state S0 a dime was entered. As you see, we do not need to create a new state. We can reuse the existing one, because the system, by being at state S2, represents the fact that it has received 10 cents. Continuing, we have a transition from S1 with a dime going to state S3, which represents the fact that the system has received a total of 15 cents. The output is still 0. And then from S2, that represents that it has received 10 cents, with another dime transition, we go to S4. Now, we also are going to augment this one to indicate that from state S3, if you get a dime, you still go to state S4, which means release. So the output on these transitions that lead to state S4, which represents delivery, will be 1, activation. So the state transition diagram is now complete because for every state it is specified what should happen when any particular of the possible inputs arrives. And this is completing also the formal specification of what the functionality of the system should be. This is the job of the state transition diagram. It simply describes the operation of the system in a detailed and precise form. Now, in order to proceed, we're going to translate this state transition diagram into a tabular form. The tabular form is going to be this one. It contains the exact same information contained in the state transition diagram. It's just in a different form. As you see, this one shows for every state what the next states are going to be under any particular input. So these combinations here represent possible inputs to the system and what is going to happen under those particular inputs. So this one here represents no dime and no nickel input. This one represents that the nickel has arrived, and of course no dime. This one represents that the dime has arrived and no nickel. This one represents the simultaneous arrival of a nickel and a dime, which is never going to happen because you can only put in the slot the coins one at a time. So this is never going to happen. That's why these entries are indicated with blanks or do not cares, okay, don't care conditions, because they're never going to show up. So this one over here contains everything that the state transition diagram has. For example, from state S0, if you get no input, you stay at state S0. If you get a nickel, you go to state 1, and if you get a dime, you go to state S2. That's exactly what this was showing. From S0, with a nickel we go to S1, and with a dime we go to S2. Similarly, from S1, you go with a nickel to S2 and to S3 with a dime. That is what this shows. So from S1, you go to S2 with a nickel and to S3 with a dime, and you stay at S1 if you receive nothing. Also, this table specifies the outputs, the possible outputs, in the exact same way. From a particular state and with a particular input, you specify what the output will be. So as you see, for example, the output will be 1 if from state S2 you get a dime. So from state S2, if you get a dime, the output should be 1. Similarly, from state S3, with either a nickel or a dime, you have an output of 1. So from state S3, either with a nickel or with a dime, you have an output of 1. So this table specifies everything that the state transition diagram specifies, but now you have it in a tabular form, and so we can then specify our algorithms for processing this information and coming up with a final design. So the first thing we need to do is we need to encode these states. We need to have binary combinations that encode these states. We have here 5 different states. From S0 to S4, there are 5 different states. Therefore, the number of bits that we're going to need in order to specify this is going to be 3. We need a minimum of 3 bits to specify codes that will be enough to represent all of the states. With n bits, you have 2 to the n possible codes. So with 3 bits, you have 8 codes, 2 to the 3, to the power of 3. And so you have enough to represent the states. If you used 2 bits, you would have 4 different codes, and so you would not be able to represent all 5 of these states. So you have to use 3 bits, and obviously with the 3 bits, since you're going to be able to specify 8 different combinations, you're going to use 5 of them and 3 are going to be unused. Now, once we assign the codes to the states, our table gets translated to this, where now the states have been replaced with their respective codes. Now, one note about the assignment: in this particular case, we have specified the states as S0, 1, 2, 3, and so the codes picked over here, or the codes assigned, I should say here, are the codes that represent the index of the state. But it doesn't have to be that way. You can assign these codes in any way you like, and in some cases, depending on how you assign the codes, things might be simpler or more complicated depending on what kind of design that you're doing. But for the purposes of our design, it's not going to matter, because we're going to use a memory and we're not going to do any optimization. So we have assigned the codes like this. Our table has now been translated to this. Now we need to transform this table yet again. We need to transform it in a form that can be written into a memory. The following steps are going to indicate how this table is going to be transformed. So for the purposes of completing the table, I have shown over here all the possible combinations of the codes that are possible, and I've specified with don't cares those entries corresponding to states that are not going to be used, or combinations, state combinations that are not going to ever appear as a state in the system with don't cares. Now, the transformation of this table to one that can be written into a memory will take place as follows. From the original table, we're going to make a new one where the inputs and the state are going to be strung together to form one single vector. So as you see, what we do here is we take the current state and we add in front the combination for the inputs, like this. Next, this is going to be augmented to add one more segment in this table, again with the states, but then with the next possible input combination. And you go on like that. This is going to be the next one, again the state, and then with the next input combination. And finally, when you're done with this process, you have produced this table here that shows the possible combinations of the dime nickel inputs and the current states. The reason for doing this is because we're going to need all of these bits to become inputs to our system eventually, and it will become evident later. So for now, what we need to do is we need to make sure that we have strung all these combinations together, the combination of current state and input, and they are all here. Further, we're going to make this one a little bit more standard, and it's going to look like this. Nothing has changed here. As you see, these combinations are still the same, but they're on single entries. So they're all finally merged with the output, to include the output as well. So this is the segment of the table that we had earlier, and we augment this to indicate the rest of the information that is on this table, which is the next state and the output. So as you see now, every entry on this table, it shows in one dimension the combination of the input and the current state and the corresponding next state and output. This table was doing it in a two-dimensional way. So state and input specifies the next state. State and particular input specifies the output. So this table is doing it in one dimension. So every entry is a completely specified one that specifies the input, the current state, the next state, and the output. Every entry. So if you keep doing this to transfer all the information from this table to this one, you get something like this. So for every combination of input and state, you get the next state and the output. And this table now will have the exact same information that this table has, it's just in a different format. So the completion of this process will produce this table. From this one, they look a little different, but they are in fact containing the exact same information. Now we're going to beautify this table a little more, and from this table, which is exactly this one, we are going to produce this one. The difference is that these entries have been merged to single codes. So in this table, the final form of the table, we're going to have an input combination that is going to represent the input and the state in a single code. Similarly, the next state and output will be represented in a single coding as well. So this one shows the complete transformation of the tables. You can pause the video if you like and look at all the particular entries if you have any particular interest in any of them, and understand how then this table is specifying everything that the original state diagram specified and the operation of the system. Next, we produce this table, which indicates how the memory that we're going to use needs to be written. These entries that represent don't cares or cases that will never appear represent blank entries. These ones are going to be the memory locations of the memory, and these are going to be the contents of those memory locations. So this is going to be used as the address of the memory, and this is going to be used as the contents of the memory in this way. Our system is using a memory, maybe a ROM, for example, and a register. The register represents the state information. So the three state signals will be the three outputs of this register, which is simply a register that latches on to the state and holds it steady until the next cycle, which will be represented by a clock pulse, which is not shown here, but a clock pulse should be produced to the register to register a new state whenever a new input happens to arrive. So the state information, as you see, is used as input to the memory. So it is fed back and it is used as input to the memory, just like the external inputs, the nickel and dime, are also used as inputs to the memory. So all of these signals represent an input address. Whatever these signals are, they specify a memory location, such as, say, this, and then the memory outputs the contents of that memory location. These outputs indicate that part of the code stored in every location is going to be fed to the register as the next state to which the register needs to latch, and whatever the output needs to be is fed to the output line. In this case, we only have one, but you can have more than one. So this is the system, the overall system, and it indicates how you can specify a sequential design using a memory with code that you write into this, hence the term microprogramming, a register, and the external inputs and the outputs. As you see, this design is universal in the sense that if you had a different state diagram for a different target machine, you could still use the same hardware architecture. So this wouldn't change. The only thing that would change would be the codes that you put in the memory. So the behavior of this whole system depends entirely on what is written into the memory, i.e. the microprogram. And that is why this technique is called microprogramming. And that is the end of this presentation. In another presentation, we're going to deal with a design of different techniques, with different techniques.